Hello and welcome to our next edition of our P4 Radiation for Life topic, and we'll be looking at radioactivity and how we can look at the positives and the negatives of radioactivity and look at the equations as well. So we'll have a look at our objectives. So for radioactivity, by the end of this lesson we'll be looking at how alpha and beta radiation are formed and how we also get a little bit of gamma radiation there, and we're also going to look at how we get the half-life of a substance and how it can be worked out. Okay, so if we start with alpha decay, what we have here is an unstable nucleus. So here we've got protons in red and neutrons in yellow, and we have decaying an alpha particle. Now an alpha particle will spontaneously leave the nucleus. So an alpha particle will leave the nucleus and fire off. Okay. Now this isn't quite an alpha particle. It's a bit tricky to get those bits out. So what I'll do is I'll pause and then I'll redo that. So here we have the alpha particle, which means this nucleus is no longer the same atom. So this nuclei here becomes a completely different nuclei because it's lost two protons. Now the protons means that it becomes the second element below in the periodic table. For example, we can see here. Now we've got Ra, which is radium, and that becomes Rn, which is radon. Now on here we've got He, because if we look closely, this is a helium nuclei. There's no electrons, which means this has a positive charge of +2. Okay, now the other way we can draw this is as an alpha sign, which is like this. So alpha and helium can interchange. So we've lost two protons, two neutrons, so the mass has gone down by 4. So the radium has turned into radon, which is 4 less, and the proton number has gone down by 2 as well. Now alpha particles, because of this strong or this high positive charge, means they are very ionizing, which means that any electron from a nearby atom could easily be absorbed. Okay, so with beta decay, what happens is a neutron decays to form a proton. Now what we have to try and think about is what a neutron is made up of. Now a neutron is made up of a proton and an electron held very, very tightly. So this here is equal to one of those. But what happens is that during beta decay, the neutron decays into a proton. So what happens to this electron here? Now this electron here comes flying out because of the massive positive charge in the nucleus and leaves the nucleus. So we have here a high energy electron. So what's happened to our unstable nuclei? Now one of the neutrons has changed into a proton. So what's happened to the proton number is it has increased by 1. But the mass has stayed the same, because relatively the proton and a neutron have the same mass. So if we have a look at an example here, we've got iodine, which is 53. So a neutron converts to a proton, so our atomic number increases to 54, which makes it xenon. And then we have the electron, which is the beta particle here. Now as with the alpha particle, because it's the same as an electron, we can write it either as an electron or we can write it as a beta particle. Now the reason why we put the -1 is because we balance up our atomic numbers here. Now the mass of an electron is 0, so we write 0. So we can see that the mass hasn't changed, but the atomic number has. Now with gamma radiation, whether it's you have an alpha decay or a beta decay, it causes the nuclei to decrease in size. Now what will happen is you will also get some loss of mass, which is barely, it's nowhere even near that 0 mark. Now that mass is given off as an electromagnetic wave in the form of gamma radiation, and we can actually work out that by Einstein's famous equation of E equals mc squared, where E is the energy, m is the mass of the nuclei that is lost in the form of energy, times c, which is the speed of light, squared. Now we're going to talk about half-life now. Now here we've got a sample of radioactive atoms or radioactive nuclei. It doesn't matter what we refer to them. Now over a period of time, the amount of these radioactive nuclei will decay, either releasing an alpha particle or perhaps releasing a beta particle. And what they will do is they will form a new sample. So this sample of atoms now has half the number of the original atoms at the top. Now this period of time is what is known as the half-life. Now the half-life is the period of time it takes for half the nuclei to decay. Now let's say, for example, this is 10 years. After 10 years again, we'll have another sample of nuclei. So after another 10 years, we've got half the number of nuclei again. Now it's not half of this amount, it's half of this amount, and it takes 10 years for this to happen. Now how we can do this is we can measure the activity. Now the activity is how much alpha particles and how many beta particles are given off in a particular amount of time. This is measured in becquerels after Henry Becquerel. Okay, so sorry, let's try and move that so we can read it. Can we read it there? Yeah. So it's named after Henry Becquerel, who discovered the half-life. So how can we calculate the half-life? Now what we can do is we can measure the activity of the radioactivity over a particular or against a length of time. Now we should nearly always get a graph that looks something like this. Now if we look at the activity at the beginning, we can see that we've got this amount of activity, and that relates to this particular time. Now from here, if we go to roughly half, now the time that it takes to do that is its half-life. Now again, if we go to half that value, then we should get roughly the same. And I think it might be my graph drawing skills. So that time there is the half-life, and that value there is the half-life. And again, we can keep going, and these half-life values will remain constant. So if we go back to our previous example, it could be 10 years here, 10 years here, and 10 years here. And it's the amount that the activity measured in becquerels will decrease over time. Now becquerels are given the symbol BQ. Okay, so let's review what we've done during this lesson. We've looked at alpha decay, where a unstable nuclei will decay to form an alpha particle, which is the same as a helium nuclei. We've looked at beta decay, where again an unstable nuclei will decay to give a high energy electron, and that's because of a neutron converting into a proton. We've looked at how we get the gamma radiation from either one of those, which is the mass lost, which is converted into energy. And then we've got the half-life calculations, where the amount of radioactive nuclei that decrease by half, every time it decreases by half, it will take the same period of time. And then we've looked at how we can measure that on a graph. Anyway, I hope you've enjoyed this, and I will see you next time. Bye-bye.